Module 10 is on bivariate data analysis. After you have done your univariate data analysis, you have already presented one by one the individual variables involved in your study. It's time to proceed to bivariate to find out if there is a significant relationship in any of the dependent and independent variables. So this is focused on Pearson or correlation. There are four areas that may influence choice of analysis, and you can determine by asking the following questions. What is the level of measurement? Remember, Noir? Are the data paired? Are they parametric? What are you looking for? Differences, correlation, etc. So each of these four we are going to tackle one by one in the next slides. What is the level of measurement? You let us mention again these four levels. So these are arranged according to level. So this is the lowest level and this is the highest level. So ratio has the characteristics of those that below it. And so with interval and ordinal and nominal has the most basic characteristics. So ratio and interval are continuous variables. You remember continuous variables? They are quantifiable. Ordinal and nominal are categorical or more on qualitative variables. The importance in knowing this is to make decisions about the type of statistical analysis that should be performed in your study. As arranged according to power, according to level. So nominal here labeled as same or not, like male or female. That's the lowest level of measurement. Going ordinal, that's higher than nominal. So it has the characteristic of nominal. It is also labeled, but rank this time. Example, second floor. So second floor is higher than the first floor, and so on. Interval higher than the ordinal. So it share the characteristics of both. It's labeled, it's ranked, and it's range. For example, a favor of 39 to 41 degrees centigrade range. Ratio, the highest of them all, is labeled, ranked, range, and zero. There is true 0 point. Like the 24-month-old baby, it's about age. So age starts at zero, same as weight and height. Are your data paired? Paired data are often the result of before and after situations. Before and after treatment, for example. Here, each research subject would have a pair of measurements. Look for a difference in these measurements to show an improvement due to the treatment. So before, weights of 30 children. Then, you introduce a month-long free feeding at a barangay health station where these children are going to eat feeding health, nutritious food for 1 month. Then you obtain the weight there after a month. So you already have each respondent would have a pair of readings of weight before this treatment and after the treatment. This would be paired data, and we can name this for our purposes of computation. Before is X and after is Y. Are your data parametric? Ranks, scores, categories generally are non-parametric data. Measurements that come from a population that is normally distributed can usually be treated as parametric if it's normally distributed. Are you looking for differences or correlation? You have two sets of data. It may not always be a sensible thing to do, but you can do it. That there is a set of paired data, just like the example we had last slide. Look for correlation. Two sets of data where each data point in the first set has a partner in the second, like the weight of child 1 before and after, and so on. Consider these 2 points. Does paracetamol lower temperature? So you see here paired information. Does the number of exercises performed affect the amount of increase in muscle strength? Here, there are two variables involved. One, paracetamol, this temperature. Now, the question is, does paracetamol lower temperature? Here, number of exercises is a variable, and then muscle strength is another variable. So what does this number of exercises do with muscle strength? Which of this is about a difference and which is on correlation? The first, about seeing difference. Does this drug make a difference? Because does it lower temperature? The second, about correlation. Does the amount of exercise correlate with muscle strength? As you do more exercise, do you have more muscle strength? Bivariate data, we already mentioned, involve two variables paired together for analysis. Educational attainment, for example, is the first variable. The another variable is income. Are these two variables related? How? Like, does educational attainment in any way affect income? The relationships here are not cause and effect relationships. They only predict the behavior of one variable from the knowledge of the other variable. Illustration. First, as a person grows taller, it is expected that he will gain weight. Is there a relationship between height and weight? Second illustration. Students are constantly spending their time studying and taking exams while going to school. Is it true that the more you study, the higher your grade will be? So imagine this bivariate pairing, so two variables. Next illustration. Research doctors test new drugs like the COVID-19 vaccine, old ones too, by prescribing different amounts of and observing the responses of their patients. Does the amount of drug prescribed determine the amount of recovery time needed by the patient? Okay. So the linear correlation, does an increase in the value of one variable cause a change in the average value of the other? Pearson correlation coefficient, represented by letter R, can take a range of values from +1 to -1. So therefore, there's in between that is point. A value of 0 indicates no association between the two variables. That's the result of the computation. A value greater than 0 indicates a positive association. Okay, like this one. If you are going to plot the two variables with the values, it will look like this for positive correlation. It will look like this for negative correlation. And if no correlation, it's as scattered as this. So there is somehow a formation of the values represented by these dots, the x-axis and the y-axis. Correlation will be considered high when it is close to +1 or close to -1, and low when it is close to 0, like this. So if R is 0.7, looks like that, 0.3 like this, 0 like that. Okay, -3, there is a relationship but negative, so it will go like this. Going down, that is negative. negative, but there is a relationship that is inverse. So if the correlation coefficients, the results of computations will be from zero point 0.9 to 1, that will be considered very highly correlated. 0.7 to zero point 0.9 highly correlated, zero point 0.5 to zero point 0.7 moderately correlated, zero point 0.3 to zero point 0.5 low correlation, less than zero point 0.3 have little if any correlation. So this will be after you have computed everything and you will have this values or results. So this is how you are going to interpret. 5 assumptions of Pearson's are the variables must be either interval or ratio measurements. Okay. The variables must be approximately normally distributed. Do first a testing for normality. The species will actually do this. There is a linear relationship between the two variables. And outliers kept to a minimum or removed when you see them. It will look like this. This is an outlier. You can remove homoscedasticity of data. It will be like this. Variances along the line of best fit remain similar as you move along the line. So the formula for Pearson R will be like this. It's a series of x and y, x's and y's. So n here, we know that n is for sample. So summation of xy, summation of x, summation of y. And there is this summation of x square and the summation of x and then you square and so on. What does a positive value for r mean? A negative value, a value of 0. As x increases and the value of y increases, r value will be positive. Okay. The positive value of r, for example, age and height of children. As a children grows older, the height will also be taller. So that is positive or a parallel relationship. So both will go up. It's still positive parallel relationship even if both will go down. As long as the two variables will have the same direction. The negative value of r, age of automobile, as car ages, its value decreases. So there is opposite direction of relationship. It is inverse. So the value of that is negative. Okay. So given X is years in school and Y is tolerance score. Suppose these are the values of X and these are the values of Y. The N is 10. So each of the respondent will have X and Y values. So you are going to total this, total, and then you multiply X by Y, you put the product here, then X square, put here, Y square, put here. So this is how you are going to do it efficiently in a manual manner. You remember when we computed the variance? So we do this and it will be faster. Okay, so already computed. 2 times 3, that's 6. 2 square, that's 4. 3, 3 square, that's 9, and so on. And then you have the total here. And it's time to transpose. Okay, in the formula. So we already know that summation of xy, it's here. Summation of xy, you just copy. So n is 10 and 675. Summation of x is 79. Summation of y is 72. And then 10. The n is 10. Summation of x is square. We have value 761. Just put it there very fast. And then summation of x, that is 79 square, and so on. Okay. Then you follow IMDAS. First, you multiply this. You have 750. You multiply the two. 5688. And below, you also multiply this, you have this. 79 square, you have this, and so on. To continue, you have now 1062 over this one, values of this. You continue, you're going to have multiply this with it, and you have this result in a million, over a million. And you obtain the square root of this. You have 1202. And now it's time to divide the final step. 1062 divided by this, and you have the value of r, which is 0.88. And where is that in the, if you're going to remember, recall the interpretation that will have a high correlation, right? Okay, that's the notices. So let us, so how to do that computation using Microsoft Excel. So you now have get given, okay, you now already have calculated this thing. So you have now the, or even if you don't have this, this is what we use in the manual, but you only need the X values and the Y values, okay? Type here, okay, the result you put here. So function here, you choose is statistical, then uh, choose person. So you need to have person, okay? Person, there is array 1, array 2. Array 1, that's the X values. Array 2, that's the Y values. Returns the person product moment correlation groups R, okay? Okay. So you specify the array 1. Array 1, that's all X. Okay, it's there. Array 2, that's all Y. And then okay. So you now have the result.